So to understand the definition on the next page, I just wanted to derive for you really quickly the equation of a tangent line in general, just one more time. I know we've done this before. So here we have a curve, y equals f of x, and I want the equation of this tangent line to the curve at the point A when x equals a, which means the y value is f of a. So the point is a, f of a. And I need to know what's the equation of this tangent line. And this tangent line I'm going to call L of x. So y equals L of x. Your author calls it L of x because we're using it as a linear approximation or the linearization of this function f of x. But it's just the equation of the tangent line. Okay, so if I have a point on the tangent line, which I do, x naught, y naught is a, f of a, and I know the slope of the tangent line, which I can find by taking the derivative, because we now know that the derivative gives us the slope of the tangent line. So it's f prime of x, but evaluated at x equals a. It's f prime of a. So I just used the point slope form, the equation of a line. I see that y minus f of a is equal to f prime of a times x minus a, or y is equal to f of a plus f prime of a times x minus a, right? Just adding f of a to both sides. So this y I'm going to call L of x. It's just a linearization. It's just the equation of the tangent line. In general, it's f of a plus f prime of a times x minus a, where I'm trying to approximate the function f of x near x equals a. So that's all this next definition says, is that is the linearization. That is the approximation. The approximating function of a function that is differentiable at x equals a near x equals a is L of x equals f of a plus f prime of a times x minus a, which I just derived for you. That's the tangent line. That's all that is. So the approximation says that f of x is really close to approximately equal to L of x near x equals a. Sometimes we call this point x equals a the center of the approximation. Okay, so what do I want to do here? Example 51. In part A, I'm asked to find the linearization of f of x equals 1 plus x at x equals 0. And then I want to use this linearization to approximate 1.2, the square root of 1.2. So I want to do this at x equals a. So x equals a, that means my a is 0. So f of a, I need f of a, I need f prime of a. That's what I need to plug into my formula for L of x, the linearization. So f of a is simply plugging in 0 into the function, which is just the square root of 1 plus 0, or 1. So then I need f prime of x, so I can figure out what f prime of a is. F prime of 0 in this case. So I need f prime of x. So to take the derivative of the square root of 1 plus x, I have to realize that that's 1 plus x to the 1/2 power, then use the chain rule. So it's 1/2 times 1 plus x to the minus 1/2 times the derivative of the inside, but the derivative of the inside is just 1. Derivative of x is just 1. So in other words, it's 1 over 2 times the square root of 1 plus x. So that means that f prime of a, because I'm thinking about it for my formula, which is f prime of 0 in this case, is 1 over 2 square root of 1 plus 0. In other words, just 1/2. So the linearization of x at x equals 0 is f of a, which is f of 0, plus f prime of a, which is f prime of 0, times x minus a, which is x minus 0. So it comes out to be 1 plus 1/2 x in this case. Now, we want to approximate the square root of 1.2. So what is the x value when I want 1.2? Notice that the original function, 1 plus x, square root of 1 plus x, I want to use that. I want to figure out what the square root of 1 plus 1.2 is. That means the x value that I'm needing to plug into my linearization is 0.2, right? Because if 1 plus x is 1.2, then x has to be 0.2. So the linearization at x equals 0.2 is 1 plus 1/2 times 0.2, which is 1.1. And then for fun, I plugged in the square root of 1.2 into my calculator to see that it's 1.095445. And so we found our approximation with this simple plugging into our linearization to be 1.1, which is a pretty darn good approximation. Notice that it's only off by 4 1/1000ths. Very good approximation. All right, let's do the same thing, same function now, but I'm changing the a value. I want my a value to be x equals 3. So I want to approximate it with a different tangent line. I'm not going to use the same tangent line that was at x equals 0. I now want the tangent line at x equals 3. And then I'm going to use that to a linearization to approximate 4.2 instead of the square root of 4.2 instead of the square root of 1.2 like we did in part A. So here a is 3. So f of a, you plug in 3, you get the square root of 1 plus 3, which is the square root of 4, 2. F prime of x again is 1 over 2 times square root of 1 plus x. So f prime of a means I plug in 3. So f prime of 3 is 1 over 2 times the square root of 1 plus 3. So that's 1 over 2 times 2, or 1/4. So my linearization now, at x equals 3 this time, is f of 3 plus f prime of 3 times x minus 3. Again, this is just the equation of the tangent line at x equals 3. So in this case, it's 2 plus 1/4 times x minus 3. If I simplify that and collect like terms, first of all, distribute the 1/4. So 2 plus 1/4 x minus 3/4. 2 minus 3/4 is 5/4 plus 1/4 x. So this is the linearization, or the tangent line, to f of x equals square root of 1 plus x at x equals 3. So now I want the square root of 1 plus x, which is the square root of 4.2. I'm going to use my linearization to approximate the square root of 4.2. So if I'm using 1 plus x to be 4.2, that means the x value I need to stick in is 3.2. So the linearization when x is 3.2 is 5/4 plus 1/4 times 3.2. This comes out to be 2.05. And for fun, I stuck the square root of 4.2 into my calculator, and I got 2.049390. The error there, geez, I'm only off by 6/10,000ths in this case, which is pretty good. And then just to show you on the graph here, here's my two tangent lines that we constructed. In part A, we constructed this guy. Part B, we constructed this guy, and it's all about constructing tangent lines near a value of x that gives us a good approximation for what we wanted. Notice if I had used this tangent line that we constructed in part A to try to approximate some value of x out here, it would have been a horrible approximation. So I had to construct a different tangent line in part B, which would now give us a good approximation near the value of x we wanted.